Okay, so our next speaker is Adrian Clingher, who is going to talk about on K3 surfaces with the lattice polarization.
All right, thank you very much. I appreciate the invitation. It's a pleasure to be able to give a lecture in this conference. I apologize for not being able to be there in person. Unfortunately, this week is our first week of school here in Missouri. All right, so I would like to talk about some specific examples, actually. This conference is about Hodge loci, so I thought I would give a talk about the K3 surfaces lattice polarization and discuss some sequence of nested moduli spaces of such objects, which will, to some extent, show some examples of Hodge loci coming up from essentially from enhancement in the Nerazzurri lattice. So first of all, this is going to be based on a series of joint works, more recently with Andreas Malmendier and Brandon Williams, but also work from some years ago with Charles Doran. At the risk of perhaps boring everyone a little bit for a few minutes, perhaps it would be instructive to recall some of the classical results on K3 surfaces. So first of all, in my talk, I'm going to look at complex algebraic K3 surfaces. So I'm going to be working over the field of complex numbers. And one of the very important object associated with these surfaces is the Néron-Severi lattice, which is essentially the lattice of algebraic cycles in the second cohomology. So that is obtained by intersecting the integral cohomology H2 with the H1 one piece of the Hodge decomposition. So this gives a lattice which is known to be even. It has a rank called the Picard rank that varies between 1 and 20. And also it has a hyperbolic type signature. That means it has a signature of this type. Of course, this lattice sits in the overall second cohomology of the K3 surface, which is known to be a lattice isomorphic with 3 copies of H and 1 E8. I should mention that for me, H stands for the rank 2 hyperbolic lattice, and E8 is going to be the rank 8 lattice associated with the E8 Dynkin diagram. So E8 here stands for a negative definite lattice. So now the concept of lattice polarization. In general algebraic geometry, we talk about polarizations or quasi-polarizations for a variety, and that is usually just one line bundle that we fix. But for K3 surfaces, or even in some other even in some other discussions, sometimes it's useful to consider a polarization that is more than just one line bundle. So in this context, the lattice polarization for me, it's going to be the following. So we're fixing a lattice, which I'm going to be call it lambda, capital lambda. And this is going to be an even lattice of a given rank. The rank has to be under 19, so we can fit it into K3 examples. And also, we would like this lattice to have a hyperbolic type signature. That means a signature of the type 1 R minus 1. So then how do we connect this with a K3 surface? A lambda polarization essentially is going to be a pair. Capital X is an algebraic K3 surface, and then I is going to be an embedding of our polarizing lattice into the Néron-Severi lattice of X. And this embedding we want to be, of course, a lattice embedding, meaning it preserves the intersection, forms the lattice pairing. But also we want it to be primitive in the sense that, for instance, if we look at the image I of lambda inside the narrow Severian, we take the quotient. There is no torsion in this quotient. A second condition we want for lattice polarizations, which connects with a regular notion of polarization, is among the classes that will be in the image I of lambda, we would like to have at least a pseudo-ample class, meaning at least a regular type polarization class. And here, pseudo-ample, it's just going to mean Neff and positive self-intersection. So two polarizations can be compared, and we're going to say that x1 I1 and x2 I2 are going to be equivalent if, first of all, there is an isomorphism between the two K3 surfaces. Let's say that isomorphism is alpha. And then this alpha also meshes nicely with a lattice isometry on lambda, meaning there is this condition. So there is a lattice isometry beta that acts on the polarizing lattice lambda, and that connects with alpha in this way. So with this concept in mind, one can actually build moduli spaces, look at periods, so on and so forth. And that goes essentially under the name of Torelli theory, as I'm sure everyone knows. So let me just briefly capture or recapitulate a few things that I will need from this Torelli theorem. So first of all, one can construct a coarse moduli space for lambda polarized K3s by just looking at local spaces of local deformations and then gluing them together. And it's known that such a moduli space, which I'm going to denote by M with index capital lambda, is a quasi-projective variety of dimension 20 minus R, where R was the rank of the polarizing lattice lambda. But then more than that, one can connect such a moduli space with periods via, we could say, Hodge theory, although Hodge theory is very simple for K3s. So basically, where are the periods coming from? If I look at the Hodge decomposition on the second cohomology, the H20 and 02 piece are one-dimensional because of the Calabi-Yau condition. And then the H11 piece is essentially the orthogonal complement to those. So one can define the so-called transcendental lattice of the K3 by, the transcendental polarization of the K3 by considering this lattice, which is the orthogonal to the image of the polarizing lattice lambda. And then the entire Hodge decomposition can actually be done on the complexification of T. So one can build a space of periods by looking at all the projective lines in the complexification of T, and there are two Hodge-Riemann conditions that are important here. Two periods, of course, satisfy the zero self-intersection and the positive intersection with the conjugate. And if we look at this space of periods, there is actually going to be two connected components. If I select one of them, and I do this by putting this plus upper index here, we get what's called a Hermitian symmetric domain of type 4. And then if we want to take into account possible automorphisms, as usual in Hodge theory, we'll have to divide by a special group. And this is going to be a special group, a special subgroup of the orthogonal group of T. Well, when we take this quotient, we get this nice space, which is called the classifying space of periods, and has dimension 20 minus R. And the very strong and powerful results here is the Torelli theorem, which says that a map connecting the two moduli spaces, the moduli space of lambda polarized K3s to the period, it's actually an isomorphism of quasi-projective varieties. So we have an identification between the two spaces. So let me go over very quickly over some very special examples of lattice polarizations that also lead to interesting geometry. And later on, I will delve into more details related to some of these examples, and we also will be examining the algebraic side. So one very standard lattice polarization for K3 is given by the rank 2 hyperbolic lattice, which, as I mentioned before, it's usually the lattice that has this intersection form 0, 1, 1, 0. Up to conjugation, that intersection form can be seen to be equivalent with this one, which we'll see in a minute why it's more relevant to us. So one interesting theorem about this type of lattice polarization is the fact that every time when you have such an H polarization on a K3 surface, that means you have a rank 2 lattice of algebraic cycles that are there. But more than that, because of the specific nature of this lattice, turns out we have a little bit more. On the K3 surface, we will actually have a Jacobian elliptic fibration. So that it means there is going to be an elliptic fibration with a fixed section. I'm going to refer to this as EFS, just in short. So elliptic fibration with section. So that means we have a pencil of elliptic curves that lives on the K3 surface and also a specific section. If we want to write this algebraically, there is, of course, the Weierstrass form of describing such an object. And in the context of K3s, we will need the two coefficients here to be polynomials in the parameter of the base in P1. And they will have to have degree 8 and 12 in order to get a K3 surface. So how does this connect with the actual H polarization? Well, every time when we have an elliptic fibration with section, there is two special algebraic classes over there. First of all, we have the class associated with fiber, which of course will have self-intersection 0. And then we have the class associated with the section, which is going to be a fixed rational curve on the K3 surface. So its self-intersection has to be -2. And of course, since we're talking about a section, the intersection between fiber and section has to be 1. So if one follows the Torelli discussion that I just did, one gets a coarse moduli space for Jacobian elliptic fibrations on a K3, which I'm going to denote by M underscore capital H. And this is going to be a nice, although fairly high dimensional variety. So this is an 18-dimensional quasi-projective variety. In the same vein, we can reduce the discussion, the dimension of the moduli space a little bit by looking at another example. So this example, it's going to be the situation when I take the rank 2 hyperbolic lattice and I add to it a very specific rank 8 lattice, which I'm going to call capital N. And this is known in the literature as the Nikulin lattice. It's very easy, excuse me, it's very easy to construct. All we have to do is take 8 generators, which are orthogonal, and their self-intersection is -2. That, of course, will create a negative definite lattice of rank 8. But in order to get the Nikulin lattice, we're going to add to this half of the sum of all these generators. So this creates a nice lattice of rank 8, which has an interesting geometric property when it appears as part of a lattice polarization. So why would we care about this? if I have a K3 surface X and I have such a rank 10 lattice polarization, then turns out that some interesting phenomenon happens. First of all, the hyperbolic piece will determine a Jacobian elliptic fibration, as we discussed just a few minutes ago. But then the Nikulin piece of the lattice will add an additional geometric part. And this geometric part is going to be, in addition to the base section of the Jacobian elliptic fibration, there is going to be an additional section that occurs. And this section is going to be a section of order 2. So basically, the geometry induced by such a lattice polarization is going to have, we have an elliptic fibration, but then there's going to be two sections. One, which I'm going to call S0, and it can be interpreted as the base of the elliptic fibration. But then there is going to be a second section, which has order 2 in the Mordell veil associated to the Jacobian elliptic fibration, which essentially means if I look at every smooth fiber, if which is an elliptic curve, and if I take the base point given by the first section, then the second section, the intersection point, will be a point of order 2 in that elliptic curve. We can, of course, write a version of the Weierstrass form for such a situation, and I have that over here. So in this picture, we have the base lattices, the lattice at infinity, but then the second lattice, the base section is the section of infinity, but then the second section appears over here. It's the section given by X equals 0. So this is a result by Nikulin and Van Himel-Sarti. The reason why I want to look in particular at this result, this particular situation is, well, if we go through the Torelli discussion, we have a nice moduli space, which in this situation is going to be 10-dimensional. But there is a little bit more than that in our situation. Because of this section of order 2 that exists in the Jacobian elliptic fibration, one can perform fiber-wide translations in the smooth fibers. And well, it turns out that those fiber-wide translations by the section of order 2, they glue together to actually lead to an involution of the overall K3 surface. So essentially what happens in the context of this elliptic fibration, I included here the generic situation when there's going to be 8 fibers of type I2, 8 fibers of type I1. I'm talking about the singular fibers in the pencil. And in this picture, you can see in green and red the two sections, the base one and the order 2 one. And well, one can translate by the red section in every smooth fiber, and this extends over the singular fibers to an overall involution. So this is going to be involution of what we call the Nikulin type, meaning that if we look at how it acts on the holomorphic two forms, it fixes them, and of course the two sections will be interchanged. So this type of involution on a K3 surface has been investigated very thoroughly, and it turns out it always has 8 fixed points. And well, if one actually takes the quotient and resolve those 8 singularities, what's interesting is we get a new K3 surface. So we start with the K3 surface X that has this type of lattice polarization H plus N. And turns out that because of this Nikulin evolution that appears after you take the quotient and you resolve the singularities, there is another K3 surface of the same type that appears, another K3 surface Y that has a canonical H plus M polarization. So this procedure of going from X to the resulting K3 surface Y goes in the literature via the name of Nikulin construction. And explicitly, it kind of works this way. I included the discussion here. So fiber-wise, why are we getting the sections on the quotient? If this is a smooth fiber, in the original K3 surface X, we have in we have in green and red the base section and the section of order 2. And well, in addition to those, there will be 2 points of order 2 in each smooth fiber, which I'm describing here in purple. So when we translate by the section of order 2, the green section and the red section will identify, and they will create a new section on the elliptic vibration on the dual K3 surface Y. And then the purple points will also get identified, and they will create a second section on Y, which one can prove that that's going to be a section of order 2 in the Jacobian elliptic vibration of Y. So the interesting phenomenon I would like to point out is every time when you have an H plus N polarization on a K3 surface X, we also get a dual, a new K3, which has the same property. So I'm going to refer to this duality as the von Neumann-Sartre-Nikulin due to the people that have been involved in uncovering it. And at the level of moduli spaces, let me recall that this moduli space was 10-dimensional. This duality boils down to an actual involution, the von Neumann-Sartre-Nikulin involution on this moduli space. So it's going to be perhaps interesting to some extent to examine what does this involution do and how various sub-loci in this moduli space move one to another. So now, after this background discussion, let me discuss in a little bit more what I want to do. So I'm going to be considering various types of lattice polarizations, but keeping in mind what I just discussed. So I would like some lattice polarization lambda with, of course, ranking between 10 and 19. And the reason why I have a lower bound of 10 is I would like these lattices to accommodate the copy of H plus N, a canonical sublattice of H plus N in there. And this will allow me to construct the moduli spaces, which will be subvarieties in the moduli space of K3s in the output H plus N. So this will be 10-dimensional, as I just discussed, and we will see various pieces that sit in here corresponding to K3 surfaces with higher lattice polarization. So what I would like to discuss is basically a look at various possibilities for lattice polarization, try to see whether one can classify those K3s. Is there an algebraic side to this Hodge theory discussion to some extent? And then, of course, perhaps, how does this duality works? If you start with a K3 with a particular type of lattice polarization, and you take the von Neumann-Sartre-Nikulin dual, what will you expect on the other side? And as we will see, there is some interesting geometry that is to be explored, and one can also classify some of these K3s quite nicely. Also, a second point of interest is, well, there seems to be also nice connections with number theory and modular forms. For instance, if I look at just a few specific examples of lattice polarizations, and I'm going to delve a little bit more into the discussion later in this talk. But let's say I want to consider an example of rank 19. So I take this particular lattice. So hyperbolic plus 2 copies of E8 plus another generator with square minus 2n, where n is just a positive integer. Well, if one goes through the Torelli discussion, through the Hodge theory, and constructs the Hodge theoretic moduli space, something interesting appears. Turns out that the moduli spaces will have to be one-dimensional is an object known to number theorists or people in modular forms. We get what's called the Fricker modular curve, which is the complex upper half plane divided by an extension of the congruence group of level n. So just to say what exactly this group is, if you take the normal congruence group of level n as a subgroup of PSL to Z, and then you add one more generator, you get this particular group, which is a subgroup of PSL to R that acts on the upper on the complex upper half plane in the usual way, and that's what we get here. So there are more interesting modular spaces that appear. For instance, if I do an example in rank 18, which I will also be discussing in details, if I drop an element from my previous example and I only consider H plus C8 plus C8 as the polarization, if I do again the period discussion, we get a two-dimensional object as the moduli space, and turns out that's another object that is known to in the modular forms world. So we get the Hilbert modular surface, which is two copies of the complex upper half plane, which are acted upon by two PSL to Z copies acting on each piece, and then we have a semi-direct product with Z over 2Z obtained from interchanging the two pieces. And if I do one more example just to show what one can get, if I do a rank 17 example by dropping one E8 and replacing it with an E7, again through the modular discussion, we get another object that is quite known. We get the Siegel modular threefold as a moduli space for this. So one point that is common to all this discussion is, well, I'm saying these are some moduli spaces that appear from out of K3 surfaces, but if we look carefully at these objects, we can see that they actually have different interpretations. All of them can be seen as moduli spaces for totally different objects. For instance, the Siegel model of threefold is known to be a moduli coarse moduli space for principally polarized abelian surfaces over complexes. The Hilbert modular surface is a coarse moduli space for pairs of elliptic curves, and the Fricker modular curve of level n can be seen as a moduli space for pairs of two elliptic curves that are related via an isogeny. So we can see from here that there are some other objects that are related to K3s, and that's another perhaps direction of research or discussion, which I'm not going to address in this talk. All these objects from the abelian variety world are not by coincidence appear in this context. There is this general theory called the Kuga-Satake theory associated with polarized K3 surfaces, which is a transcendental construction that associates abelian varieties to a polarized K3 surface. And what we see here is some very, very low levels. Anyway, so I guess what I wanted to say so far is these 2 points of view, the relation with modular forms and also this Van Hemel-Sartre-Nikulin duality these were one of the theories that me and my collaborator found interesting to study in details. Moduli spaces for lattice polarized K3 surfaces, and in addition to trying to maybe do a classification, examine how their moduli spaces would sit in the context of the larger 10-dimensional moduli space for H plus n polarization. So now, after this background, let me delve into some actual examples and examine, in addition to the Hodge theory side that I just talked about, examine the algebraic side. That means try to construct these K3 surfaces explicitly via perhaps some equations. Excuse me. So the first example that I would like to talk about is a rank 19 example. So I'm going to pick a very special rank 19 lattice, hyperbolic, plus 2 copies of E8, plus an A1, which essentially means just one generator with square minus 2. Note that this is a special example in the context of what I discussed here. When you take n equals 1 and the moduli space, then it's going to be just the moduli space of complex upper half plane divided by SL2Z. So from the point of periods or Hodge theory, if we wish to call it that way, well, these K3 surfaces will have a nice one-dimensional moduli space, and via periods, this can be identified with complex upper half plane divided by PSL2Z, which is the same as the moduli space for elliptic curves over complexes. So if one asks, well, what are these special K3 surfaces? Can we actually construct them explicitly? It turns out the answer is yes, and one can actually give a very nice construction for them. So since we know that the moduli space looks like the moduli space of elliptic curves, why don't we start with an elliptic curve over complexes? And I'm going to write that in the Weierstrass form. So we have these two coefficients, G2 and G3, and we want the discriminant delta to be non-zero, so in order to have a smooth elliptic curve. Well, it turns out that based on this information, you can construct a K3 surface as a special quartic in a projective 3 space. So I'm looking at this particular special quartic equation. It might look a bit complicated at this point, but if you look carefully, you can see there's just two coefficients, G2 and G3, that appear. Well, three of them, sorry. You also have the discriminant, but that is a function of G2 and G3. And it also, although we're dealing with a quartic, to some extent, it mimics the Weierstrass equation of this, of the elliptic curve via, if you want to look at this part of the quartic. So nevertheless, what I want to say is that if I look at this two-dimensional family of quartics, G2 and G3, they are not going to be smooth. There is going to be actually two singularities that always occur, but those singularities are not going to be a problem. One can resolve those singularities. And then when we take the minimal resolution, what comes out is an actual K3 surface, which has rank 19 generically, and the canonical polarization that comes out is exactly the one that was claimed. So this is a theorem that myself and Charles Doran proved a while ago, although the format of this particular equation is not really ours. We built on this family also previous work of Shioda and Inose, which analyze such quartic equations, but in the context of K3 surfaces of rank 20. So now you may ask, well, I said earlier that the moduli space here is one-dimensional, but I'm dealing with a family with two variables, G2 and G3. Well, it turns out that that is actually not a problem. Turns out that if I look at these K3 families, this K3 family, and if I want to compare two members of the family corresponding to two pairs of coefficient G2, G3, then we get exactly the situation from the Weierstrass form of an elliptic curve. So the two K3s will be isomorphic precisely when the two original elliptic curves were isomorphic. That means when the two coefficients are related to each other via this weighted projective condition. So, not surprisingly, then this particular space is going to be a coarse moduli space for both H plus E plus E plus A1 polarized K3s. Well, it requires a little bit of proof, but that turns out to be the case. And of course, that is also the known moduli space, coarse moduli space for elliptic curves. This particular family of K3s, I skipped 2 slides. I just wanted to say that actually has some very interesting geometry. If we want to examine all the rational curves that occur in the generic situation, turns out that we have a nice configuration of 24 rational curves that occur, and they are organized. They can be organized in this particular diagram that you can see here on the screen. So in this particular picture, I wanted to organize the diagram so you can see the actual H plus E plus E plus A1 polarization. So H corresponds to an elliptic vibration with section, with the section being at the blue point A1, capital A1. The two E8s will correspond to two E8 type fibers in this elliptic vibration, which you can see in purple throughout the diagram. And then the additional section is going to be in green. The Nikulin evolution I was talking about earlier in the context of these K3 surfaces is actually one of the symmetry of the, you can see it as one of the flips in this triangles. For instance, the way I constructed the polarization of the previous slide, and you can see the Nikulin evolution as this interchange that flips the triangle over this axis that kind of goes a little bit up to the right. There is more to say about this family, but I'm going to stop here as far as this example goes. In fact, if you look at the automorphism of this type of K3 surfaces, I believe the generic automorphism group has order 6. It also have an automorphism of order 3, as you can see in the symmetry of this triangle family. The last thing I want to say about this example is, well, what is the Van Given-Sartre-Nikulin dual? Well, it turns out that if you go through the Nikulin construction in the context of the quartic equation I just described, then one can actually construct explicitly the quotient and then resolve the quotient. And something quite interesting comes up if you look at this quotient, which I'm going to call Y, depending on the two parameters G1 and G2. Turns out that that's actually a Kummer surface. And not surprisingly, it's the Kummer surface associated to a product of an elliptic curve to itself, the elliptic curve being exactly the one that we started a discussion. So that actually also shows how you can see the elliptic curve we started with in the context of a geometry. All right, so this was a rank 19 example. Let me move a little bit down in rank and discuss a rank 18 example, H plus E8 plus E8. I should say that any polarization from the previous example, H plus E8 plus E8 plus A1, of course, carries a rank 18 polarization of this type. So the previous moduli space is going to appear as a sub-loci, a sub-variety in the moduli space we're going to discuss next. So this is one of the examples I mentioned briefly several minutes ago. If you do the Hodge theory associated with this example, the moduli space of periods turns out to be a surface, and not surprisingly, turns out to be the Hilbert modulus surface. So now the algebraic part, can we construct explicitly this kind of Cater surfaces? And turns out the answer is actually yes, and it's a situation that is perhaps simpler than what we had in the previous example. So all we have to do is essentially decouple those three parameters from the previous quartic. So I take a quartic equation of exactly the same time as we had before, but now the three coefficients, which I'm going to use, I'm going to call the A, B, and D. There's not going to be any a priori relation for those. So D is no longer the discriminant of G2 and G3 as in the previous example. But turns out the discussion I had before, so the setup of the theorem I had before stands. So again, this family of projective quartic curves, they carry some singularities that one can actually describe explicitly. And those are going to be rational double points. So one can take nice resolutions. And the minimal resolution turns out to be a Cater surface, which I'm going to denote by capital X, depending on the three parameters A, B, and D. And with a little bit of care, one can see that actually this Cater surface has the polarization claimed at the top. So it's a rank 18 polarization of that H plus E8 plus E8. And how can one convince themselves of this? Well, one situation, one possibility is to just follow through the resolution of singularities and see what rational curves occur. Well, it turns out that when you do the resolution of singularities, in the generic case, these K3 surfaces will have a nice 19 curve configuration, and the dual diagram corresponding to the intersections is given here. I'm copying this diagram twice because on the top I would like to show how one can see explicitly the H plus E8 plus E8 polarization. So in purple you see the two E8 copies, the two E8 Deligne diagrams. And then the H piece comes from an elliptic fibration with section. So we have these two fibers, elliptic fibers. These are singular fibers in the elliptic pencil. And then in the middle, this is going to be a section. So this determines an elliptic fibration with section, which takes care of the hyperbolic piece. What is the Nikulin involution that I was claiming earlier? Well, as you can see, this 19 curve configuration has a left to right symmetry. So if you flip it over, this is exactly what the Nikulin involution does. And the elliptic fibration that carries this Nikulin involution has a singular fiber of type I12 star or B16 in the in the linking diagram discussion, which you can see here in red. And the two sections from the from the H plus N polarization, you can see in the lower diagram in blue. So one section, say the one on the left, can be seen as the base section, and then the one on the right, the blue dot on the right, can be seen as the section of orbit. So basically, this all these K3 surfaces, they carry two elliptic fibration with section, one coming from the H plus C8 polarization, and the other one from this another embedding of H that sits in this lattice, which is not isomorphic with the first, which gives the evolution. So now one can ask the question we had before. Well, what I'm describing here is a family with three parameters, but the moduli space is supposed to be two-dimensional. So what's going on? Well, it turns out that something maybe to be expected or quite nice is happening. So first of all these quartic surfaces that I just constructed, they cover all possibilities. And then if you want to see exactly when two quartics correspond to isomorphic K3 surfaces, well, it turns out that there is a weighted projective condition that relates to triples. So the A coefficients are related via a weighted projective condition of weight 2, the B coefficients via weighted condition of weight 3, and then D via weighted condition of weight 6. And in this context, if I look at this moduli space, if I look at this particular space of weighted projectives, one can prove that this is actually the coarse moduli space for these polarized K3 surfaces. And well, how does this relate to the Hilbert modular surface that I had before? Well, it turns out that one can actually compute explicitly the period map, essentially the inverse period map. So the map that goes from the Hilbert modular space or surface to the weighted projective space I just discussed earlier. So if you take the Hilbert modular surface and you maybe put some coordinates there, say tau 1 and tau 2 are the coordinates on the cover, then it turns out that these three weighted projective coefficients are related with the periods in this nice form. So we have the G2 and G3 functions and the discriminant delta for both tau 1 and tau 2. G2 and G3, of course, can be seen via modular forms as coming from the two standard Eisenstein series E4 and E6. And of course, delta, then it's going to be associated to G2 and G3. But I should point out that this equation, tau 1 and tau 2 now are decoupled. So we no longer were dealing with just one elliptic curve. And well, if we look at this, Hodge theory says this K3 should be related perhaps to a pair of two elliptic curves. Turns out that is not coincidental. If you do the von Giemel-Sartin and Nikulin discussion and we look at the dual K3 surface, well, it turns out that dual K3 surface is again a Kummer, but now it's a Kummer of a product of two independent elliptic curves. And what are those two independent elliptic curves? They are exactly given by the G2 and G3 from above. And if one wants to relate directly with the ABD, there are these nice formulas that one can have. So the product with the two J invariants of those elliptic curves turns out to be this quotient. Why my pen doesn't see it. So this quotient A to the cube over D and the sum of the two J invariants correspond to A to the cube by d squared plus d, everything divided by d. So bottom line, this this family of rank 18 K3s relates to pairs of two elliptic curves, and you can classify everything explicitly via quadratic equations. To go to the next example, maybe I'll go a bit faster. When am I supposed to finish? How much time do I have left?
Like 1 minute, I think.
Oh, okay. Okay, sorry about that. Looks like I
Okay.
totally
We started
overshot.
a little bit later, so maybe 5 minutes.
Okay. All right. So I'm gonna go then very fast over the next examples, and if anyone wants to see the details, I'll be happy to share the slides with them. So basically, one can do the same thing in rank 17 for this polarization 8 plus E8 plus E7. Again, you can construct all these K3s via quartic equations, and as I said before, the moduli space now, it's going to be the Ziegler modulo threefold, which also corresponds to abelian surfaces. Well, turns out that the coefficients in the quartic equations are known modulo forms due to Gusa, and the Van-Giemel-Sarti equation, the Van-Giemel-Sarti Nikulin duality actually recovers the Kummer of an abelian surface. So what I wanted to say, and I'm going to go faster over this example, all this discussion, I was planning to present several separate examples in details. The same discussion I have done for rank 19 and 18 examples, one can actually do for a full range of lattices, not just for what we had before. So one can ask, well, is this going to generalize somehow? Well, turns out that you can look at very special lattice polarization that will accommodate this Nikulin involutions. And the most obvious situation is when you consider lattice polarization, which are of two elementary type. So two elementary, to remind you, means a lattice for which, when you look at the discriminant group is z over 2z to a particular power. That's the condition for a lattice to be two elementary. And the power, this power I'm going to call length. And then there is a nice theory of Nikulin that actually classifies all these two elementary lattices. So turns out there is three invariants for two elementary lattices. You have the rank, of course, of the lattice. You have this length, which says how many z over 2z you have in the discriminant group. And there is a third invariant called parity, which essentially says how the discriminant form is. Normally, the discriminant form of a lattice takes values into q over 2z, but if it takes values actually into z over 2z, we're going to say the parity is 0, otherwise the parity is 1. So Nikulin has done this this classification of the two elementary lattices, and I have a picture here that shows how you can map these lattices according to rank and length. And then one can also examine, well, in terms of K3 surfaces, what kind of elliptic vibrations can you get there? What kind of sections? So what are the situations essentially when you can have this H plus N polarization, this Nikulin involution? And turns out that if you impose this condition and you say, well, let's also look at K3 surfaces that have finite isomorphism group, turns out there is a nice list of lattices that appears. So you have in every rank from 11 to 19, one possible choice. These were the two choices I have discussed already. And I was going to talk a little bit about these two before going into the general theory. The only rank where we have two lattices that may appear is rank 14, which turns out to be quite interesting. So what I would like to say is that in recent work with Andreas Malmendier and Brandon Williams, we have gone through all these examples and we have done an analysis kind of similar to the discussion I briefly have done for these examples. And you can see those lattices that can occur in this particular picture. As you can imagine, when you go down in rank, the description becomes a little bit more complicated in both terms of the quartic that you would like to construct. But with a little bit of care, you can actually fit those quartic equations and look at their coefficients and see that, well, the coefficients have actually a strong modular form interpretation. So just to give you a very brief example, for instance, I have here one of the rank 18s. This is a situation when the transcendental lattice is h plus h for plus 4 copies of E1s. Well, this is a rank 18 situation, but one can do a classification similar to what I talked about before. So one can construct some quartic surfaces with a little bit of care, but this time they will depend on 10 coefficients with some conditions. And well, one can look at these quartics, identify the singularities that may occur, resolve the singularities, and then one gets a K3 surface that has the polarization I'm claiming, that rank 14 polarization. Well, I was going to discuss a little bit how the singularization goes. Earlier, we were looking at special curve configurations. In this rank 14, we also get a 27 curve configuration that carries some properties, but of course, it looks a little bit more complicated than what we had before. Nevertheless, I include this picture here if anybody would like to at some point look at this example. Bottom line, in addition to being able to construct all these K3 surfaces, turns out that there is also this strong modular form flavor in the construction. With a little bit of care, if we pay attention to these quartics and analyze the symmetries that occur, one can define some invariants, which I'm listing here. So A, B, C, and all the other coefficients were the 10 coefficients of those quartics. And well, it turns out that those invariants actually correspond to modular forms corresponding to this Hermitian symmetric domain of type 4. So this is an observation that we found myself and Andreas Malmendier. We show that you can construct a weighted coarse moduli space coming up from these coefficients. And then in work with Brandon Williams, we were able to show that these are actually modular forms for this Hermitian symmetric domain of type 4, and they actually generate the ring of modular forms of the even weight ring of modular forms. Anyway, I'm running out of time. If anybody is interested in all this discussion of what I said in all these examples, I will be happy to share the slides. And in case anybody is interested in the actual papers, these are the archive codes for the papers. Sorry for going over time. I'm going to stop here. And if there are any questions, I'll be happy to answer.